to our fourth session of Protective Relay School Class webinar, Generator Stator Ground Fault Protection with Jack Chang. My name is Monica Gevorgian, and I will be moderating today's call. First and foremost, whether you are working from home, from an office, or factory, we hope that you and your families are safe, healthy, and are practicing good measures to remain so. Before we get started, I'd like to go over a few housekeeping items. Please refer to Q&A widget to submit any questions that you have during the presentation. We will address as many questions as possible during our webcast, and in case we don't get to your question, we will send out answers as a follow-up. You will have an opportunity to receive your exclusive certificate after 40 minutes from the start of our webinar, and please download it right from the presentation deck through the widget located on the right side of your screen. Keep in mind that this presentation is being recorded and it will be shared following the broadcast. Moving on to technical issues. Since some of you may be working from home, we expect a few more technical issues than normal. So if you are experiencing any audio or visual difficulties, please pay attention to the following tips so that you have the best experience today. First, close all other applications and internet browser tabs to increase your bandwidth. If you start having issues, first try refreshing your browser window by pushing the F5 key. You can also try to log in out from your VPN, which tends to slow down your operating speed, as well as switching to the Google Chrome browser if available to you. If you don't have any Google Chrome, the second best options are Mozilla Firefox and then Microsoft Edge. Moving forward, I would like to introduce our speaker today. Our presenter today is Jack Chang, Regional Technical Manager at Hitachi ABB. Jack will be available at the end of the presentation to answer your burning questions. Thank you, and enjoy the webinar. Jack?
Thank you, Monica. Hope you can all hear me well. Thank you for attending this year's the webinar series. Monica mentioned this is the fourth one. And we will be diving a little bit deeper into the generator stator ground fault protections. So in previous years, annually we presented pretty much the same protection webinar from ABB and Hitachi ABB. At that time, really the information is more or less the same for the last few years. So this year we decided to have a change to see what other topic or specialty of the same topic that we can provide to our customers on the marketplace. And so for generator protections, instead of the regular the generator protection webinar tutorials governing all the different aspects of generator protections, from the field, from the rotor, from the stator, all the way. Instead of that, now we will more focus on just the ground fault protection on the generator stator. So the agenda for today, I hope I can complete this in time to leave some time for Q&A. So I'll do my best here. So for the agenda, I plan to touch on the four major points. One is the common generator station layout and grounding designs. Two is generator grounding types and considerations. Three, we'll dive deeper in more details into the protection schemes for the unit-connected high-resistance grounded generator, which is most commonly found in large utility units. And the last, we will conclude with the protection schemes for low resistance and reactance grounded generators. So the reference material, I put some screenshots here. They are public available IEEE. That's very, very informational. Most of my presentations are actually extracted from these guys. There's one more is the PSRC published tutorial for generator protection. That's very useful too. If you are a protection engineer actually setting up a generator protection relay, that's a very useful resource. So first, on the electrical equipment layout, on the right-hand side, you will see this figure is illustrating a typical power station, power plant. And so you have the generator, you have your turbines, and then you have your excitation system, and then the generator usually is connected to a unit transformers, and from the unit transformer you connect it to your high voltage system. So there are two types of connection of the generator. One is typically what we commonly see for utility larger units is unit connection. Unit connection can come with or without a dedicated generator breaker. If it comes without a generator breaker, typically you will utilize the high voltage line breaker, bus breakers as its generator breakers. But in that case, typically you also have a disconnect switch so that you have a means to isolate the generator, and you are able to restore the bus section, high voltage bus section back to service. So the advantage to have a generator circuit breaker, dedicated breaker, is so auxiliary service loads, such as those pumps, those motors, that can be driven and supplied by the utility. Utility fee in case the generator goes down. So that's the advantage. Generators are typically high resistance or resonant grounded to reduce fault currents and allow the most sensitive protection. We will provide more details on this. So this is for high resistance grounding and the unit connected type of connections. The other one is typically in the more industrial setting, smaller MVA, smaller capacity generators. The generators are typically connected via shared buses. So, that means you have more than one generator parallel together through the same bus. Or you share one, multiple generators can share a low voltage transformer winding. That's possible too. But and also the generator can be parallel together and connected directly to a utility distribution feeders. That's also common. So any this type of connections is typically low resistance and reactance grounded to facilitate selective relaying. So that because to facilitate selective relay, you need a reasonable amount of fault currents available. So you cannot restrict the fault current to too low a level. So that the protection the coordination can be made possible. So typically it's driven by feeder grounding choices. So like if the feeder system, distribution system is low resistance grounded, typically your generator will be low resistance grounded as well. Okay, and we'll touch more about this later, just to give you an idea of the different the plant connection in the generation plant. So why are we grounding a generator, power generator? There are three objectives, basically. First is to reduce the stator core damage, basically stator core and winding damage from internal ground fault. As we know, the zero sequence impedance for a generator actually is smaller than the positive sequence. In other words, during the ground fault, if you don't limit the current, it will be actually higher than the three-phase fault for the single phase to ground, for example. Okay, so that's why typically we would like to add some kind of impedance in the neutral to limit the ground fault current. And then the energy generated by a ground fault can be expressed or modeled by the I square R times T is the duration of the fault. So you can see by this mathematical expression, if the most efficient way to lower the energy generated would be by lowering the current, because there's a square root, there's a square right there. However, the other factor is that the fault current will continue to flow even after you trip the generator, trip the turbine, open the turbine, open the valve if it's a hydro, and open the field breaker, disable the field. Even if you do that, the fault current does not stop right away because there's an inertia, there's a trap flux inside the core that would that would enable the fault current to continue to flow for a few seconds, for example. And if the fault current is not controlled, is not managed, then that could easily damage the generator core. So that's the main reason. The other one I briefly touched upon is to limit mechanical stress. Basically, the idea is generator, the zero sequence react typically smaller than subtransient, which is we use to calculate a three-phase fault. It's a positive reactance. So if you add a neutral grounding resistor to the neutral, you constitute as a larger component for the zero sequence branch, zero sequence network. And that would actually effectively limit the ground fault current below that of the three-phase current. That's the idea. The third is limiting transient overvoltage on generator installations. Okay, because all the apparatus connected to generator terminals, such as the buswork, the transformer windings, these auxiliary transformer cables, should withstand temporary overvoltages. Okay, surge arrestor as well should also be rated. So if you refer to the guide, you add if you do not if the generator is left ungrounded, there will be very high temporary overvoltage during line to ground fault. So that's why you always want to add certain amount of neutral reactance in the neutral, and then based on these two bullets, there's a way the certain amount of a neutral reactance that you can limit the overvoltage to a acceptable level. For example, if we just focus on the second bullet, that's for reactor grounded system. The third bullet is high resistive ground system generator, so pure resistance, neutral resistance. Typically, the selection is to keep that resistance the same or a little bit smaller than the equivalent zero sequence capacitance of your network connected to the generator terminals. Okay, so in that case, you will limit the overvoltage to 260%. The other comment is on the grounding type associated to the choice of relaying. So the grounding type are typically associated with generator system configuration. So it's unit connections. I mentioned in the previous slide, is either unit connection or the bus with feeders or bus together a couple generator in parallel. So the idea is, to summarize is that those resulting to low ground fault current is generally considered to be able to maximize generator protection. Okay, for example, if you high resisted grounded a generator, typically you limit that fault current to a very low level. You enable a very sensitive protection to that generator. However, that you are not able to coordinate the protection with any other. It's hard for you to coordinate with other downstream protections. So higher ground fault current, if you allow higher ground fault current, generally are necessary to allow a selective relaying scheme. Okay, for example, if you have multiple generator bus together, then you want to make sure your protection are coordinated, because when the fault happens inside the generator or near the generator, for that particular unit, you do not want it to you do not want the protection of other generator to operate, and the only way for you to selectively distinguish that is to have sufficient fault currents. So if we progress to the next slide, so there are different generator grounding types exist on the that's commonly used. Some of them are actually some of them are more commonly used than the others. Okay, so in the order of increasing ground fault current, so basically we have resonant grounded as the which will result in the lowest amount of ground fault currents, which most effectively limit the ground fault currents. On the contrary, on the other end of the spectrum, the solid grounded system basically yields the maximum amount of fault current, because you are not actually limiting the fault capacity, the fault current. ground fault current. So to go into a little bit of detail, resonant grounded on utility typically utility large machines, especially in Europe, you will see this resonant ground a lot. And in North America, not so much, but I have found some papers describing in United States, especially there's some installation of resonant grounded. It has its advantage, okay. But the idea is basically it's grounded instead with a resistor. It's grounded with the large reactor, and this reactor can be tuned, okay, so that it's flexible. It can be tuned. Well, first of all, this reactor actually is located on the secondary distribution transformer, just very similar to a high resistance grounded principle. But instead of a resistor, there's a reactor there. But the reactor it can be tuned. The idea is you will offset. You will need to know the capacitive reactance of the generator system. That includes all the capacitance from the winding, from the bus bar, etc., and from the transformer winding. So everywhere else are connected to a generator terminal. You need to know that. And then the idea is to tune a reactor to offset that capacitance, zero sequence capacitance. And then the result is a very high equivalent resistance. Okay, that's much higher than the one used in high resistance grounding. So the result of that, of course, then is the fault current will be limited to a very, very low value. It's less than 1 amp typically. Okay, and because of such a low fault current, it cannot sustain an arc. So that's why typically the reason for choosing this type of grounding is so that your system is critical, that you would like to have a choice. You do, whenever there's a ground fault happen, you do not want it to trip right away. You actually would like the operator can have a choice to make a planned shutdown depending on the plan, so that you do not interrupt the supply, disrupt the supply right away. Instead, you are given a choice because the ground fault current is so small. Okay. However, there still runs the risk of a second ground fault hitting. In that case, you will actually become the face-to-face fault, and then you will incur a very, very high fault current. But however, this will give you an opportunity to orderly shut down the generator instead of being tripped directly by the sections. Okay. So you can see low iron damage because the current is so small. However, the other advantage of that is this, because of such a high resulting equivalent resistance. Now, actually, you can consider that now is actually grounding the generator. The sensitivity of your 59G or your over voltage protection can be that much sensitive as well. In other words, it can detect a much higher fault resistance than the high resistance grounded protection could. Okay. In other words, if your winding insulation to ground start to deteriorate, this type of resonant grounded scheme protection might be able to detect it ahead of time before it develop into a ground fault. But however, for high resistance, it's not possible. So the sensitivity is much higher. Okay. Ungrounded, it's very rare. Typically, for ungrounded, you either will put a high resistor there, or a high inductance like resonant ground. So really, very rarely used. Okay, and high transient line to ground voltage will ensue. High resistance grounded we'll discuss in more detail later, because it's the more common way of grounding the generator, at least in North America utilities, in Canada for sure. So that we will discuss a little bit more detail, so I don't provide more the information here. Low resistance grounded, the neutral current is typically limited. You select the resistor to limit the neutral current a few hundred amp to 1.5 times the generator rated current. Because you have that significant amount of generator current, the fault currents there, the differential protection could operate for most of the fault along the winding. Okay, so which is a good thing. So and with maybe another type of differential like restricted earth fault, like ground differential relay on the winding, you set that up. Maybe you can protect almost down to the neutral. It can be very sensitive because your fault current is high. I mentioned this a few times already. The protection selectivity can be maintained with this way. And low inductance is very similar to low resistance. The idea is to limit the line to ground fault current to values less than 3-phase fault. So whether to use which of these, I do not have the experience, but the literature I read is it depends on the feeder system, the distribution system. Solid grounded is also not very commonly used. So typically, if you decide to allow the very high fault current, then you would typically opt for the low resistance grounded or low inductance grounded type of establishment. Okay. Here I have another note here is the order. This order is reversed. Okay, you completely reverse it in terms of the level of temporary and transient overvoltage. So in other words, with solid grounded, you get almost no transient voltage, overvoltage, but with ungrounded or resonant grounded, you will get a very high level of overvoltage, temporary overvoltage. Okay, so we'll go into a little bit of detail on the grounding type with high resistance grounding. So most commonly deployed for large generation units across North America. Right, resistor connected can limit the fault level. Usually the the grounding resistor is selected to limit the fault level to 5 to 25 amp. Okay, 5 to 25 amp typically is not sufficient to operate most phase differential relays. So when you have phase to ground fault, you typically the phase differential 87G basically, that's not typically going to operate on this. Not sensitive enough. So there are two methods to achieve this type of grounding. One is effective grounding via distribution transformer. This is more commonly used than the other one because only a small grounding resistor, typically less than 1 ohm, is needed on the secondary side of this grounding transformer, the DT. If you can see my mouse, this is basically the type of scheme, the grounding scheme with the DT, and then the resistor is on the secondary side of the DT. Because as you remember, when this resistor's resistance value is reflected to the primary side, you need to multiply by the return ratio of this DT square root of that term ratio. So that basically magnify that resistance. So that's why this resistance can be kept fairly small in small values. So it's more economical. Or the other method, which is rarely used in North America, is directly connect to the neutral. If you direct connect the resistors in neutral, you achieve the same result, but however, you need a much bigger resistor in the kilo ohm range. And this fact I mentioned it to keep transient overvoltage. That try to select the resistor so that the capacitance to ground, the system equivalent capacitance to ground over your selected grounding resistor is about 1 or slightly larger than 1. The distributing transformer typically are rated a little bit higher, need to be rated higher than the phase to ground voltage of your generator. So typically it's selected to the line-to-line rating of the nearest class below the generator rating. For example, if the generator is 15 kV, then typically your distribution transformer is selected for 14.4. Because your phase to neutral rating for that generator is about, I think it's 8 kV, so 14.4 is substantially larger. So, okay, the next couple slides we'll dive into the protection scheme of this type of grounding. Okay, actually we have a poll.
Thank you, Jack, and hello again, everyone. You have an opportunity to answer our poll question regarding grounding type or types you have experienced. Please read the question and choose the best option that is suitable. You will have 15 seconds to submit your question. Your answer, I'm sorry. Jack, please see the results from poll question to discuss. Thank you. They are ready.
Thank you, Monica. Yeah, actually this is expected. High resistance grounded, 65%, most of it, as I mentioned, at least what I have seen so far. Resonant grounded, I see 17.5% and low resistance grounded. Most low resistance grounded probably is industrial, is installed in the industrial setting. Correct me if I'm wrong during the Q&A. That's all. Thank you for taking the polls. So let's move on to the protection schemes of high resistance or resonant ground protection scheme. Actually, based on my understanding, the same type of protection scheme apply for both. Okay, so and I will only mention the protection scheme from now on. The characteristic of both of these type of grounding, as I mentioned before, is the results they produce very low fault current. Right, the phase differential protection generally is not sensitive. The stator ground fault current decrease linearly for fault at terminal towards the neutral. So at the terminal, if the fault right on the terminal, you get a maximum fault current. But even with the high resistance, you only get maximum for 25 amp, depending on the size of your resistor. For resonant ground schemes, you get even less, like less than 1 amp. So that's for the fault on the terminal. But if the fault is not on the terminal side of the generator, you're actually on the middle of the winding or somewhere in the winding, and the worst is towards the neutral, close to the neutral, you basically get no current, almost no current, right? So the ground fault near the neutral produces zero current regardless of grounding type. So any given protection type, it's important to know that you will not cover 100%. Okay, so because while you approach the neutral, you got less and less current. So there's a point that it goes beyond your sensitivity of a protection, regardless how sensitive your protection is. You just cannot cover 100%. The other protection principle needed to work in tandem, or sometimes you will see this primary or backup. There are three types of protection schemes commonly applied to high resistance and resonant grounding protection schemes: neutral over voltage over current, or the NC number 59G, 51G, or the third harmonic based, or the neutral injection principle. These three are most commonly found to be applied on this type of grounding, generator grounding design. So first, we'll discuss the 59G and 51G, aka the 95% stator ground. Okay, these type of protection can typically only cover up to 95%, but of course this is just approximations, right? So depending on your setting, depending on the ratio of your distribution transformer, depending on the size of your resistor, the maximum fault current, you could maybe go to 97% or so, but the idea is you're not going to cover 100%. You need something else to cover that remaining portion of the winding. Okay, so for PP9G, single line to ground fault at generator terminal will impress the full rated line to neutral voltage on the neutral. Okay, the reason for that is because your neutral grounding resistance is so high, it's much higher than your positive and negative sequence impedance in your symmetric component network. So they can be ignored. So really, most of the entire the generator single line to ground voltage is actually applied directly to your grounding resistor, and also of course the capacitor as well, the system capacitor. But because the protection are measured only across this grounding resistor, so you only need to concern about the current or voltage you measure across that neutral neutral impedance. The fault magnitude decrease moving toward the neutral. Okay, so because the currents reduce, your voltage measure will also reduce. So typically, when you're down to the certain point at the neutral, you cannot detect, maybe down to the 5% as I explained. This type of protection relay, typically in modern numerical relays, it is actually filter only the fundamental frequency, just like any other typical distance differential relays. The only measures fundamental frequency. You actually filter out every other harmonic. It's measured via the VT or directly on the distributing transformer secondary across the grounding resistor. Okay, so this just basically depending on the type of grounding design. Like if the ground director is directly on the neutral, inserted in the neutral, then you need a VT. If it's using a distribution transformer, which is typically found in North America, then you measure directly out of the DT secondary. But you need to apply time delay to coordinate with the terminal side VT secondary fuse, because for secondary for the VT fuse to ground, line to ground fault on the secondary conductors, your fuse VT, you need to let VT fuse to operate first. You do not want your generator to operate trip, or you sometimes need to coordinate with system ground fault as well. For resonant ground system, 59G typically only alarm. Okay, I mentioned before, to allow a more orderly shutdown. Okay, because iron burning is not a concern because the fault current is so low, and it is also more. It can provide a much more sensitive coverage than the high resistance grounded design. Okay, I mentioned that before, because the effective resistance due to resonant grounding is a lot higher. I think it's 100 times higher or something. So you can measure a much higher voltage across that resistor. So you can detect incipient insulation deterioration, for example, sometimes. Equally applicable are the overcurrent protections. You basically have CTs either in the neutral or in the secondary side, as illustrated by these two figures. So this CT is directly on the neutral, just like your, typically how we do transformer, neutral backup protection, or you can be on the DT on the secondary side. Okay, so the idea is the same. And also the same type of it can also capable of measuring down to maybe 95%. From the literature, actually, the 5051G is typically is a little bit less sensitive than the 59G in general. Okay, so same coordination requirements. Okay. You can set up a 50G, which is instantaneous high set, used to ensure high-speed clearance of line-to-line ground. So I think this is the repetition. Both of these protection are tuned or filtered to measure fundamental frequency only. You'll ignore every other harmonic content. Okay, so this is 59V9G. Then because it cannot measure 100% of the winding, you need another method to cover the remaining of the windings, right? So we have two other ways. One is the third harmonic, one is the injections. So here's the third harmonic. The goal is to detect faults close to neutral. Okay, the reason to detect is not because the fault level, because fault level for either of these is the fault current is quite small, right? But it is the increased likelihood of the second fault, because remember there's an overvoltage stress on your insulations for base to ground. So you would like to stop that situation as soon as you can. Right? So the idea is this: the previous scheme, the 59G and 59G and 51G, actually can measure from the terminal end of a generator down to, let's say, 95% using the typical values, right? So it leaves the 5% remaining on the generator winding from the neutral unprotected, right? So the idea for this is you need to look at the other way, that I need to protect that remaining 5% from the neutral. So this is the purpose of the other 100% Stator ground protection. And these type of protection cannot then protect the whole winding either. They only protect from the neutral all the way, from the neutral up. So in other words, the two protections, the 59G, for example, and the third harmonic method need to overlap to provide a full 100% protection on the Stator winding. Okay. Some characteristics on the third harmonic. Okay. The third harmonic content for voltages behaves very similar to zero sequence. Okay, zero sequence quantities. The magnitudes are equal in phase for each of the three phases. So that basically is the same as zero sequence. And the magnitude varies. Okay, so not every machine can produce the same amount of third harmonic voltage content. Okay, some may not even produce enough. Okay, so not all generators are designed to produce sufficient third harmonic voltage. So that's why it's important to understand. Typically, it need to be done through testing. You run the machine in different operating conditions, different loading, different loads to make sure you have sufficient. What is your lowest harmonic voltage, third harmonic voltage, low voltage, third harmonic voltage that the generator can produce, and what is the highest? Typically, that can only be obtained from field measurements. Okay. But typically, you requires about 1% for this protection scheme to be effective. Okay. So the third harmonic characteristic, it differs from loading under normal conditions. From this figure, these figures are actually in that in the tutorial, in the PSRC tutorial. It has very good figures here. So the idea, as you can see, that under different loading conditions, you have a different third harmonic. And then we are measuring the third harmonic voltage from the neutral and from the terminal side. Okay. So that's why it only shows the voltage level at the neutral and the terminal side. And based on different load levels, different loading, you can see they are different. Okay. The characteristic to detect the fault at the neutral is that when the fault happened right at the neutral, okay, your 59G or 51G will not detect anything because there's no values. There's very, very low fault current and developing very negligible fault voltage, right? The zero sequence voltage, neutral voltage. But on the case for third harmonic, for the fault right at the neutral, you can see that actually the third harmonic voltage reduces. It becomes zero, almost zero, close to zero at the neutral when the fault is at the neutral. And on the terminal side, if you measure the third harmonic voltage there on the terminal, it actually increased. This is the difference for third harmonic compared to the fundamental measurement of the voltage. Okay, and this is how this scheme is based on. Okay, so there are three schemes, okay, coming out of it: 27, 59, and 59 THD. Okay, so typically this type of third harmonic scheme is able to cover up to 10 to 30% of the winding from the neutral. So it's not from the terminal, it's from the neutral, and you will overlap with 59G and 51G to achieve 100%. Okay, first we'll go through the 27 and then the 59, and then kind of the differential comparator schemes. We'll summarize them. So first of all, you need to have, because you measure the neutral voltage, so this protection is tuned or filtered to measure third harmonic voltage in the neutral VT or DT. Okay, basically it's the same place where you measure that 59G. Okay, the same place, except that 59G you filter out the fundamental component, and this requires the third harmonic. 180 hertz for a 60 hertz system. So it's based on the principle of neutral third harmonic voltage reduction. So the fault is in the neutral, you will actually reduce. So basically, this is an under voltage type of application, right? So when your neutral measure third harmonic voltage is below your set point, then it means there's a fault close to the neutral, right? And then you want to operate. Okay, so now you can detect the fault close to the neutral that your 59G cannot. The disadvantage is, for this method, you need to have the excitation on and also the voltage applied. Otherwise, you won't measure anything. If the generator does not produce enough third harmonic, you could you could erroneously trip your generator due to 27 third harmonic. That's why typically it needs to be blocked when doing startup or shut down when the excitation is not on. Okay, or typically it needs to be supervised by a 59 relay. Just when the voltage is above a certain level, right, when the excitation is on, you release these protections. Otherwise, you don't allow it to operate. This is the disadvantage. And for some machines, sometimes you need to be supervised by a power relay or overcurrent relay. In that, during certain load conditions, load is too low, you do not receive enough, enough current. It doesn't produce enough harmonic content. You need to block that as well. Okay. For 59, you do not have this problem. The 59 depends on the elevations of the voltage at the terminal end, right? So you do not for the fault close to neutral, the terminal voltage actually increase. Okay, so that's why you do not have to supervise it. However, the disadvantage is that you requires a three-phase VT, because you need a three-phase VT to kind of measure the zero sequence component, which is kind of equivalent to a third harmonic. But for modern numerical relays, the Y-Y connection is okay, because the relay can calculate the zero sequence components, inside directly. Okay, and last is for third harmonic differential. Okay, the idea is that the ratio of the third harmonic voltage between the terminal and neutral is usually constant, relatively constant under normal conditions. Okay, when fault hits near the neutral, the balance was disrupted. So the sensitivity is greatest for fault at each end, lowest near the middle. Okay, so there are certain points in the winding that you won't detect anything, but that's okay, because those points typically are covered by the 59 or the 51. It requires voltage measurement at the neutral point as well as open delta zero sequence. So basically, it requires a measuring point from both of these 27 and 59, so that you can do a differential comparison. And then basically, you require some field trial or commissioning as well. During commissioning, you need to know how much this, you can consider that as your slope, right? How sensitive or how biased you want your slope, just like how you set up a differential protection for transformer or a generator. You need to know. So the more the lower the slope, or the more sensitive. The higher slope, the less sensitive. And the less sensitive means you will cover less amount of winding. Okay, so that's the idea. The advantage of this scheme is that it's operational. You know, it does not need to be blocked during generator startup and shutdown. Okay, I'm a little bit behind, so I will quickly use the next 5 minutes to go through this type of injection-based solution. Typically, you inject some sort of signal. Typically, is a current with certain frequency. On the marketplace today, most other manufacturers injected with the 15 to 20 hertz. You see 20 hertz a lot. Stop harmonic into the stator via the neutral distribution transformer, the neutral transformer, grounding transformer, or you can inject into the terminal broken tail that connects VT. But it's not so common. The more commonly done is directly through the neutral. Okay, and then you measure the voltage, and based on Ohm's law, you can calculate the impedance. Okay, and then based on the impedance, you can compare. Okay, so you trip when it's low, too low. Too low means there's a fault. So that's how you do that. This is the fundamental principle is rather simple. You inject the current source, you measure the voltage, and then you find the effective impedance, calculate effective impedance. The advantage for any injection scheme is that you can detect fault in 100% of the winding, all the way to the low voltage side of a step-up transformer. It does not require excitation applied. It does not, so that you do not need to block when the generator is ramping up and shutting down. Okay, and you actually protect when the generator is even offline in standstill is offline, and it's operational across all load levels, voltage or frequency. The disadvantage is you need those additional equipment, and those are, you can consider them as extra point of failure, right? You need spare for them. So those are part of your protection system as well. It's possible to have redundant N1, N2 protection, but typically, with only one injecting source, you can have two measuring relay doing the measurements, but typically you will only have one source. And very, very rarely, or I don't think it's even possible to have, typically we do N1, N2, we want it to be redundant from different vendors, right? I'm not sure in this case it's even possible without interfering with each other. It's some research yet to be done or proven. In this case, 95% stator ground fault protection acts as a backup, because actually this type of protection can protect the entire winding on its own. So the 95 is actually just a backup in this. So this is basically the general descriptions of this type of technology. And the next couple slides is actually will focus more on the HAPG injection solutions. Okay, that's us, HAPG, Hitachi ABB Power Grids. So we do have our own solutions. So again, we need an injection module. I have a better figure after, a bigger figures. 062 is the coupling resistor unit. It's used when maximum voltage posed by the generator is bigger than the 120 volt. Usually is 240. So you typically need this equipment. And the relay, REG670 is the relay, is the measuring device, calculating and doing the tripping. And then we have a signal injection transformer that increase protection margins, reduce the loss when you inject. If you inject through the regular distribution transformer, not designed for this type of injection, you need to really be careful, because the gain or the signal loss could be higher, right? So we have a dedicated a signal injection transformer where you just inject that into that transformer instead of through the distribution transformer. It eliminates interference to other connected protection in neutral as well. And our injection is higher, 130 hertz actually, so it's not a subharmonic frequency. It's due to our corporate research. proving that this type of frequency will incur less interference from, say, harmonics. So this is a more graphical figure. So this is the laptop running the commissioning tools, which I will describe a little bit. And then you have your relay here, right? The measuring. This is your injection source, and then this is your coupling resistor, and then your injection transformer injecting into the stator. So the injection source and the in the way that it feeds the measured currents and voltage back to the protection relay for calculation. Okay, so this is the same figure here with a little more detailing explanations here. So I'm not going in the detail because the short of time. However, I just want to point you out that you can see the main components. These are the relay measuring, and you use the regular voltage inputs. You have 3 of them. The 2 are for the current and voltage, and the other one is for the 95% 59G VT source, VT inputs. And then you have the injection source here. You have your coupling resistor, your injection transformer. You directly inject it into the neutral. Okay, so how it is. I would just like to touch on the principle here a little bit, so as to get your understanding. So the impedance at a generator neutral can be modeled as shunt winding capacitance, reactance, and other connected equipment together. So in other words, all your shunt impedance, including your equivalent capacitance to ground, are actually modeled as a parallel impedances. Okay, and then they are in parallel with your fault resistance. So in mathematically, you can express in a way that your measured, which is your total equivalent capacitance, is your fault resistance in parallel with your everything else, basically your system impedance. Okay, and then based on this impression, then you can actually calculate your fault resistance by your measured and your known system impedance, right? And then REG 670 calculated is based on you injection the signal, you measure the current, and then basically you find that measure capacitance. And these K1, K2, these values can be resolved, can be found during commissioning using our tools. Okay, and multiple, because the machine is operated through different conditions, such as ramp up, synchronizing to the grid, or even once it's synchronized, it's running through different loading. So all these will create different actually equivalent impedance, the Z reference. So there are multiple Z references you can actually define in the settings, and then you can actually switch them by logic internally, depending on your running operating conditions. So this will give you the most optimized calculation test result. And of course, and this calculated final fault resistance value will be compared with your set point, either it's alarm and trip, to make the alarm and trip decisions. Okay, and this is the tool. Basically, this is an automated tool where it's part of our PCN 600 doing the commissioning, using for the commissioning and defining definition of these different parameters. And we have a very detailed commissioning manual for this. So that a very good detail is right there. So we're not going to go into this on details. It looks like we have the final poll.
Yes, thank you, Jack, and hello again, everyone. You have another question coming up here regarding your company's experience with ground fault protection. Please read the question and choose the best option that is applicable. You have a couple of seconds to submit your answer. Dear Jack, here we go with the poll results. Please see the results on your screen. Thank you.
Yeah, this is within my expectation as well. Most utility has attempted to do this third harmonic voltage-based schemes, but however, as I mentioned, the catch is that not every generator can generate enough third harmonic contents level to effectively for the user to apply the third harmonic scheme, right? So that need to be tested and verified live in field tests. External injection, some attendees seem to have experience, but this is actually start to gain its popularity right now, just due to the disadvantage of a third harmonic voltage-based system. Okay, my final slide here is on low impedance ground protection schemes. As I mentioned before, low resistance typically limit the currents to a couple hundred amps all the way up to 1.5 times of the rated generator current. So there are a substantial amount of current. So typically you can use differential protection to detect, and then coincide with maybe a ground differential, which is also now known as restricted earth fault, to detect those. The other note is that for protection during startup and shutdown, because the frequencies start to increase and decrease during that time, your typical differential protection may not be effective due to the frequency issue, because as I mentioned, differential protection typically only effective around that fundamental frequency 60 or 50 hertz range. So some type of frequency deviations, some type of in modern numerical relay, there's a frequency tracking features available that you can enable to allow the protection be more sensitive during that frequency excursion stage. Okay. Sorry, it takes a lot more time than I thought, but this is the end of my presentations. I can look at some questions. If I am not able to complete all, I'm able to answer them through email as well. You can always contact me. Yes, Monica?
Yes, thank you, Jack. So we have a lot of questions coming up here. Let's do one or two, and then we will definitely send all answers by email as a follow-up. Here is the first question from Norik Mikoyan. What is the basis in choosing generator neutral grounding? Does it depend on generator rating?
No, I don't think it depends on generator rating. I think it depends, first of all, on the criticality of these generators, right? So if it's very critical utility machine, you definitely don't want it to be damaged. So that's why typically in large utility generators, you typically ground it in a way that you limit the fault current with high resistance or high reductance grounding, okay, to avoid that damage. So it really depends on how critical this machine is, and also depends on the type of system you are connecting the generator to. For example, you connect it directly to the feeders, then the feeder typically are low resistance grounded, because then your generator has to be low resistance grounded. Okay, so there's a multiple way to answer this question.
Thank you, Jack. And another question from the same person. How is the first ground fault detected in ungrounded generator?
You won't be able to detect the fault in an ungrounded generator, as far as I understand, because if it is ungrounded, the first fault, it basically is like a ground. So it's like a ground. So applied to that generator, so there's no fault currents. So you won't be able to detect it, but that's the danger, because then your line to ground voltage will elevate. That will actually stress on your insulation. So if insulation failed, right, you will actually will deteriorate to a point that it becomes the face-to-face fault. So that's the danger. That's why this type of practice is not commonly used. ungrounded. To my
Thank you,
understanding.
Jack. And the last question that we will be able to answer today, will injection from Sarah. So the question is, will injection method works for generators that are parallel to the same JSU, different winding?
Different winding, probably, yes. But like in our perspective, like when we recommend the customers, we typically, well, I have to think more about this question if it's parallel to the same GSU, the different winding. Typically, our requirement is that it has to be unit connected. Means there's only one winding. Okay, so if it's parallel to the same different delta winding, I have to. You probably because the other winding, the other generator connect to the other winding probably will be connected because of that delta connection. So I have to draw out the symmetric components network to clearly answer your question, but my guts tell me no, because that's our practice.
Thank you very much, Jack. If you want to conclude the webinar and then say goodbye to our audience, as we are running out of time already.
Sure. If there's these questions, Monica, will you send me or
Yes, sure. We will follow up with them for definitely.
Sure, I can try to. If you have your email here, I will try to spend time answering them.
Yes.
Yeah. I did.
Sure.
Okay, but yeah, thank you for attending, everyone. Yeah, for your time.
Thank you, Jack, and I want to thank you everyone for joining our webinar today, and also would like to invite you to our next webinar session about the transformers protection taking place on September 23rd. The link you can see on your screen. Thank you again, Jack, for the great presentation. I wish you everyone to stay safe and have a great rest of the day. Thanks again, and goodbye.